physicists, thanks for coming back for just a little more information. This is the last piece of our introduction to 5.2 in work and power. We're going to focus on power. So we talked during the work video about the definition of work, and we said that work was equal to change in energy. That's an important idea, an important concept, but when it gets down to it, a lot of times we care about how fast that energy is changing as well. And to focus on that, we're looking really at this idea of power. Doing power calculations and doing problems like this really are generally pretty straightforward. The idea of power is defined as the change in energy per time. It's just a rate, okay? Or because we know the work energy theorem, we can also write that as work per time. When we're focused on units, which is always something good when you're making calculations, we need to know what the units of power are. So power is measured in watts, W-A-T-T-S, watts, the measure of power. That's how I always remember. It's marked with a capital W. The only tricky thing here is that work, the variable work, is marked with a capital W, and the unit for power is written with a capital W. So just keep in mind so you don't get those two things confused. A watt, 1 watt, is equal to 1 joule per second. So it's a pretty easy unit conversion. If you just want to write it as joules per second, that's okay as well. All right, let's take a look at a quick problem here just to make sure that we know how to apply all of this information. So this question says, a 1,000 kilogram car accelerates from 88 meters per second to 100 meters per second in 30 seconds. How much power does that require? So we're going to go through this just with our nice guess method for good measure. So we know the mass of the car is 1,000 kilograms. We know the initial velocity of the car is 88 meters per second, and the final velocity for the car is 100 meters per second. It says that this all takes place in a time of 30 seconds. The unknown here, it says how much power, so power is our unknown. Given's unknown equation is the next thing that we need to do, and we've got an equation right here for power. We say that power is equal to the change in energy divided by time. Now, when we look at our givens, we don't have any energy in the list, but we can think through and understand what kinds of energy we might have. So it doesn't say anything about going up or down a hill or a ramp, so that would imply that our gravitational energy is not changing. There's no mention of springs or stretchy things like a rubber band, so no elastic energy, which means that the change in energy that we're really focused on is just kinetic energy. So we're really going to say something here like the energy that is kinetic at the end minus the kinetic energy at the beginning divided by time will give us our power. So that's 1/2 mv final squared minus 1/2 mv initial squared divided by time. And you can, if you want, factor out that 1/2. I'm going to do that here mostly to show you something that's really important when you're doing problems like this or when you're doing work problems. You need to make sure that you write this as VF squared minus VI squared, and it is not VF minus VI quantity squared. Those numbers don't work out the same way, okay? So you have to square them first before you find the difference. So now that we've done that, let's go ahead and plug in our numbers here. So we've got power be equal to 1/2 times the mass, which is 1,000 kilograms, times, that's going to be 100 squared minus 88 squared divided by our 30 seconds. These are in meters per second, by the way. Sorry about that. All right, then I'm going to go ahead and plug that into my calculator. You can do the same. So 0.5 times 1,000 times 100 squared minus 88 squared, and then divide that by the 30 seconds. And that gives us a total power that the motor had to provide of 37,600 watts. There's power.